and both are very impressive in what they've achieved in their expertise. Tim Palmer is a Royal Society Research Professor in Climate Physics from the University of Oxford, and he pioneered the probabilistic ensemble forecasting techniques for weather and climate prediction. And he now calls for a CERN for climate change. He will give us a 10-minute presentation of this, after which we will have Peter Bauer, who's the director of DestinE Earth. DestinE Earth, if you haven't heard of it, I'd recommend looking it up as well, is developing a global-scale, highly accurate digital model of the Earth to monitor and predict the interaction between natural phenomena and human activities. And this will be followed by a discussion between the two of them.
Hi.
Thanks both for joining us.
Great. Good to be there virtually, or be here virtually, whatever the right phrase is.
Wonderful. So Tim's going to start us off.
Okay, well, I mean, this is a discussion about climate change, and at the heart of climate change is fairly basic physics. We're emitting greenhouse gases into the atmosphere. We basically understand pretty well what that does at the large scale, which is to say it's warming the planet. We know that. We know some sort of simple things which are consequent on that, which is that a warmer atmosphere typically holds more water, sort of water evaporated from the ocean. So when we get intense storms and such like, the rainfall amounts tend to be considerably larger than we have experienced before. And we're seeing that all around the world. Everywhere pretty much the planet's warming, and everywhere where we get intense rainfall, we see it's intensified yet further. The Pakistan floods perhaps being the most recent example. But beyond that, trying to pin down exactly what climate change means at the regional level, whether it's in Canada or UK or indeed Pakistan or Africa or pretty much anywhere regionally, is a very, very, very complex problem. And what I mean by that is to know whether, for example, the predominant problem is going to be one of enhanced heat waves and drought, leading to food crop failure and such like, and enhanced wildfires. That's one scenario. Another one is increased storminess and flooding, which is a completely different one. And if you're a country or a region trying to decide on what type of infrastructure you need to adapt to climate change, then it is important to know whether you're predominantly heading for a hotter, drier climate or a wetter, stormier climate. This affects, the type, whether you put in flood defenses or enhanced reservoirs or whatever. So we understand pretty well with our equations of physics and the models we've developed, we understand pretty well about climate change on the global scale, but we don't understand nearly so well. There are considerable uncertainties about modeling climate at the regional scale. And it's not really because we kind of don't understand the physics of the problem. It's just that the equations are devilishly difficult to solve, and they need literally the world's largest supercomputers. And both Peter and I have a background where we've worked in operational weather forecast centers, where over the years, Moore's law, which is basically the fact that computers double in speed every couple of years for the same electrical and financial cost, it's meant that we have been able to see the benefits of increasing the resolution, what we call the resolution of the models. In other words, how much detail we can put into the models, how much of the local circulations we can represent explicitly. And we can see that, clearly in the skills scores, how accurate the weather forecasts have become over the last several decades, purely because we have been able to develop finer resolution global forecast models with much more detail. And that's kind of transformed our ability to forecast extreme weather events a week ahead. I mean, we're now forecasting a week ahead, what a few decades earlier, we'd only be able to do a day ahead. So with weather forecasting, we can see very clearly the benefits of enhanced resolution models. And both Peter and I and a group of our colleagues feel that this level of detail needs to be brought to the climate change problem if we're really going to tackle this question of what type of what climate adaptation means to individual countries. And incidentally, there's a kind of a related problem, which is people sometimes talk about a plan B for climate change if we can't agree on mitigation, which is what's called climate geoengineering, where we spray sulfate aerosols into the stratosphere to try to block sunlight. But again, this is actually a more complicated problem than one might think at first sight, because the climate change problem is essentially a problem of not enough infrared radiation leaving the Earth warming up as a result of insufficient infrared radiation leaving the Earth, whereas blocking sunlight is doing something at the visible and ultraviolet end of the solar spectrum. So the two are not equivalent. One does not necessarily balance the other. And again, we've got sort of questions about whether climate geoengineering might do something really unexpected, like diverting the monsoons or changing the moisture flow into the rainforests, and this would have really adverse effects. And again, can only answer these questions with models which we feel comfortable that are producing reliable results. So as I say, Peter and I and a group of us have been for a few years now advocating for considerably enhanced modeling capabilities to really try to get the resolution of climate models down to, the so-called grid scale of a climate model down to something on the order of a kilometer or so. And Peter actually is leading now a big EU project, which is doing precisely this. It's just started a few months ago. So this is a great step in the right direction that the EU has decided to undertake. But coupled with this is the problem that to actually really see the benefits of this, we need dedicated supercomputing that can run these very high resolution models. And we're just entering the era of exascale supercomputing, 10 to the 18 floating point operations per second. And to really make use of all this research and development that Peter and his team in Bonn are doing, we need this sort of dedicated exascale computing. So a few years ago, I kind of coined this phrase of a CERN for climate change. We need something like a CERN for climate change, something which has international support to create the type of, particularly to fund the type of dedicated exascale computing that would allow us to run these new generation of 1 kilometer scale climate models of the type that Peter is developing under the Destination Earth project. And we haven't yet got there, I would say. We're still, looking for international partners who would sign up to this. The cost is not great by comparison with, satellite missions and things like that. Very small money compared to the James Webb Telescope or something like the Large Hadron Collider, but something that I think is vital for our society as we're heading into climate change. I can talk a bit more about this, but I think perhaps that just sets the basic tone, if you like. Peter, do you want to take over?
Yeah, thank you. Yeah, this pretty much summarizes the science case, just like Tim has presented it. And the evidence for this has been recently shown when some of these, experimental simulations at those scales have been run, and you can see actually that not everything falls into place, and just by increasing resolution, all the errors go away. But you see that all of a sudden, if you run simulations like this in the atmosphere, the ocean, or sea ice, you see that certain processes and the feedback between processes becomes a lot more realistic than in present-day climate models. So while resolution will not solve all the problems, it's certainly a necessary element of solving these problems. So without enhancing resolution, we will not overcome key errors in our climate predictions that we have today. And I think this is important to recognize. So resolution is certainly one important part of the equation. And that translates immediately into computing. But before I go on and talk about Destination Earth, maybe I should add another little story that Tim indirectly referred to already. So in Europe, we have this European Center for Medium Range Weather Forecasts, and Tim was a leading scientist at that center, and I'm still working there. And it was founded nearly 50 years ago. And it was founded with the thinking that you pool your scientific and intellectual, but also funding in some place to kind of advance together on something, a leading idea that no individual country could do on its own. And as Tim was saying, you know, the creation of ECMWF at the time was a big success in weather prediction, and we can measure that, and we have been measuring this over decades, how skill improved as a consequence of ECMWF's foundation and this pooling of resources, intellectual and monetary. So it's a success model. We know that this kind of scheme works. And you know, an anecdote from that time was that at that time, the breakthrough thinking was, hence the name of ECMWF, is that we break the barrier of sufficient predictive skill for extremes, for example, into the medium range, which is like, let's say, a week ahead. At that time, you know, forecasts probably dropped their skill after day 2 or 3 to something useless. You know, today we have these levels at like day 7, 8, or 9. And many countries actually who eventually contributed to ECMWF at the time actually didn't believe that this was possible. And still they were convinced that, you know, if you pooled these resources, you could pull this off. And 50 years later now, we actually have the evidence and proof that it can be done. So this template worked for weather. And the idea is to translate the same concept to climate. Climate right now is research driven. So it is not operationalized to the same level as NWP is. And it requires the same dedication in terms of HPC, so high performance computing, data handling, and the pooling of resources in terms of, you know, scientific excellence, computational science excellence, and the link to adaptation and so forth. And this is what this idea is about. So Destination Earth is doing this right now as a project funded by the European Commission. So there is a project, and you could say, oh, that's fine. But as Tim was saying, we're struggling to find sufficient computing resources because while Destination Earth has funding and is distributing funding across like Europe in this case, so it's trying to pool excellence in a certain way, it doesn't have a dedicated supercomputer in a single place like what we have at ECMWF for weather, for example. So we have to request allocation partitions here, there, and put this together and try to fulfill what we actually require in terms of the computing. So despite Destination Earth's existence, there's a long way to go in terms of this commitment of science and technology that we require for a challenge of the scale of climate change. And one thing I want to add to that is that our thinking has already moved forward beyond the simple prediction task. Right now, we're actually thinking into creating an entirely new information system where the science and technology question that we covered already to a certain degree is included, but where we want to take this to the next stage, which is what we call digital twins. So eventually we want to create a fully interactive simulation system where scientists and users can interact with that system, at the core of which sits a simulation capability that relies on this outstanding supercomputers, but where you create an entirely different data universe that includes actually impact sectors like food, water, health, risk management as part of the Earth system. So move beyond the physical limits of the Earth system into the human system and create an interactive system that actually translates what we know as extremes into the impacts for society so that we can deal with that. So we have really advanced these ideas over the years, and we believe that it takes actions like Destination Earth to start, but we need more to create the actual critical mass, and that goes well beyond what we can do in Europe. It needs an international stage.
I mean, perhaps I could just throw in an example of perhaps what we're talking about that's very topical at the moment, which is the devastating flooding which has occurred in Pakistan this summer, a really kind of supercharged monsoon. And, you know, a lot of commentators, and indeed, I think the relevant minister for Pakistan has said quite unambiguously that, you know, we're seeing the effects of climate change. And in one sense, they're right, which is that, as I mentioned, you know, in my earlier when I was speaking, that a very sort of rudimentary, if you like, element of climate change is the fact that the air is warmer, and warmer air can hold more moisture. So when, you know, you get an intense monsoon, climate change can exacerbate it. So, you know, a natural conclusion you might want to draw from this is that these types of flooding events are going to become more prevalent in the future over Pakistan, and therefore Pakistan has got to adapt to a much wetter climate. But actually that is not necessarily the right conclusion to draw. And the reason is that when you, I mean, look, for example, this year at what the primary drivers of the enhanced monsoon were. The primary drivers are actually coming from anomalous conditions in the oceans. And most important of these is the so-called El Nino event in the Pacific Ocean, which for the last couple of years, and it's projected to go into a third year, has been in what's called the negative phase, or the La Nina phase, where sea temperatures in the eastern equatorial or near equatorial Pacific Ocean have actually been cooler than average. And this drives a kind of a global, or at least in the tropical latitudes, a global circulation, which has intensified the monsoon circulations, particularly over Pakistan. And in fact, the ECMWF seasonal forecasts, which try to predict both the development of El Nino and La Nina events and their consequences around the world, correctly predicted that this summer would be an intense monsoon year for Pakistan. So the primary driver this year was the La Nina event, but it was exacerbated by what I would call the thermodynamic effect of climate change, which is to say the fact the air is warmer and more moist, and therefore that will intensify an already wet summer season. However, the question of whether we can expect this to become a kind of a norm under climate change is not a simple question, because one has to be able to also answer the question, does climate change, in other words, does our emissions of CO2, is it going to affect the likelihood of the El Nino event or the La Nina event, or indeed other types of ocean anomalies, for example, directly in the Indian Ocean? For example, if climate change is leading to a more prevalence of El Nino events, the opposite of La Nina, then that actually will suppress these intense monsoons. So one can put it like this, that there are sort of two phases to climate change. One we're starting to see already, which is the thermodynamic effect of a warmer, more moist atmosphere. But there's a sort of second effect, which will certainly be kicking in soon, which is how climate change is affecting the dynamics, the circulation patterns in the atmosphere and in the oceans. And if we're to answer the question about whether flooding is becoming more prevalent will become more prevalent in say, Pakistan, understanding this dynamical feedback, how CO2, enhanced CO2 is affecting these large-scale ocean atmosphere circulations like La Nina, El Nino, is critically important. You know, you just cannot answer the question of Pakistan without knowing the answer to that question. The problem is when you look at the current generation of climate models, the ones that feed into the IPCC reports, they are completely in disagreement about this. There is no consensus at all. And if you look at the monsoon, some predict wetter monsoons, some predict drier monsoons. When it comes to the dynamics of the climate system and the impact of CO2 on the dynamics of the climate system, then current generation models are not doing a good job. And the reason is that they rely on rather ad hoc parameterizations of processes which we believe to be important and which could be resolved with a 1 kilometer grid, but instead are having to be represented in a rather simplified way. And different models have different parameterizations, and therefore they end up with different outcomes. The same, incidentally, is true in California. You know, we're sort of, just the fact there's been this La Nina for the last couple of years, we're sort of, you know, the commentators are sort of assuming that climate change is going to lead to a kind of a perpetual, you know, wildfires and drought. But again, if ultimately we see that we switch into a more permanent El Nino phase, the opposite of what's currently happening in the tropical Pacific, then the implications for California would be completely different. So these are kind of order one questions about the future of our climate system under climate change that we just can't answer at the moment because the models are just not good enough at getting the details of the interactions between the atmosphere and the oceans on small scales and how they feed up to large scales adequately. And that's why Peter's project, I think, is absolutely critical to getting a much better, really a quantum leap in our understanding of the longer term effects of climate change, just beyond this simple thermodynamic effect. But as Peter says, we need the computer hardware to go with it. Otherwise, the software developments, we won't be able to take advantage of them. So that's why we're kind of pushing for this, if you like to call it CERN for climate change, whatever the words you want, but some kind of international facility that would kind of mirror perhaps what ECMWF did for weather prediction, but for climate.
So one experience we make once in a while is that at political level, we hear that, you know, okay, we all accept climate change is happening. And then you have, of course, you know, examples like what Tim just mentioned about California, where people just extrapolate present events into the future and say, what's bad now gets worse. It must be like this because warming gets worse. And so they call actually the science discussion over, and they say, we all know it's going to get warmer. The models agree, and that's the end of it. No further funding needed or no further effort needed in the science world. And what we're saying is, while this is true for the temperature question, so for the in simplified terms, you know, radiation coming in, radiation going out, the infrared radiation being trapped following the greenhouse gas increase in the atmosphere, and therefore the near surface atmosphere and the surface warming, the models, the existing climate models agree on this, you know, and that's good. But if you take the next step and you say, and now I want to know what happens at regional or local level, or what it means in terms of precipitation, what it means in droughts, what it means in extremes, like the combination of droughts and heat waves, or extreme rainfall events leading to flooding, or extreme storms, causing coastal flooding or something. As soon as you move away from the warming part, the models disagree, and this is where the breakthrough needs to happen, because most of the impacts are felt at local and regional level in terms of a flash flood happening here or a drought heat wave happening there. And at the local and regional level is also that's also the scale where decisions are being made. So if a German government, or let's say a European government, wants to define or design their emergency response plan for the next 10 years, or they want to drive the Green Deal. The Green Deal in Europe is a €1 trillion investment over a decade or so to achieve carbon neutral Europe in the next until 2030. That's a structural investment of €1 trillion in changing industry, in changing energy provision, in changing building regulations, everything. You can think of agriculture, flood protection, everything. For driving these decisions, what you're going to do in Spain, what you're going to do near the coastlines in Northern Europe, what you're going to do in the UK. These decisions need much more reliable input at those scales and on the effects that matter in terms of precipitation. So everything but temperature, really. And this is what we're saying here. We need that breakthrough. We need that breakthrough in scale. We need that breakthrough in predictive skill at multi-decadal level, the levels where the decisions we make now show an impact. We have to bring together the science with the impact sectors more, the energy, food, water, and decision-making levels. And for this, we require an information system. And this is what the climate CERN is going to provide, and what DestinE Is starting, but needs more momentum to build up. So I think we know what to do. What we're lacking is that critical mass of funding and agreement on this purpose. And as Tim was saying, given the multi-billion impacts that climate change already have today, and what's projected to be, I think, about 70 billion per year by a Deloitte study recently, an information system that's going to cost you, I don't know, a couple of $100 million seems to be comparatively cheap. Don't you agree?
I mean, it's worth saying Peter was a lead author on a very important paper in Nature a few years back. But the title of the paper was kind of interesting, and I think, I don't know exactly, it was something like The Quiet Revolution of Numerical Weather Prediction. And it's worth just saying a few words about that, because I don't think people, it's a bit like Al Gore's, metaphor of a frog, put a frog into water and turn the heat temperature up. And the frog sort of never quite notices that the temperature is getting warmer and warmer until it's too late. This is a bit like that, but in reverse, in the sense that weather prediction, if you go back 50 years or so, in fact, it's interesting. If you go back to the 1970s, then you find that tropical cyclones killed literally hundreds of thousands of people at a time. One sufficiently intense tropical cyclone in the 1970s could kill hundreds of thousands of people because there was no warning whatsoever of this. And over the years, we have got better and better and better at forecasting not only tropical cyclones, but cyclones that become extratropical. ECMWF famously produced a fantastic forecast of how the superstorm Sandy would completely track back from its normal route across the Atlantic and end up hitting New York a week before this thing happened. And people kind of, I think, just take this kind of week-long forecast for granted. But it's come from an enormous amount of high-tech mathematics, computer science, and actual computers, as well as advances in satellite technology. It's been a kind of it's not been a kind of revolution because it's happened slowly, and it's happened sort of behind people's radars, but it's just been happening over the years to the extent that whereas in the 70s, we didn't even know what was going to happen tomorrow. We can now pretty accurately predict a week ahead. And when we can't predict accurately, is something I've worked on much of my life, we give credible estimates of uncertainty. So you see these cones of uncertainty now for tropical cyclones, because not only do we estimate the most likely development, but what is the kind of range of uncertainty. And these things have revolutionized the way in which disaster relief agencies and humanitarian agencies now work, in the sense that they now are moving into a phase where they take precautionary or what they call anticipatory action based on the forecasts, because they know the forecasts are now reliable enough that they can trust them to send food and shelter and medicine and water and stuff, shelters and so on, into areas that are predicted to be affected by extreme events. So this has been a kind of a slow burn, as it were, kind of revolution that's occurred over the last few decades. And it's happened because, you know, I think irrespective of politics, governments have realized that weather prediction is important for making, you know, society resilient to extreme weather. Now, with climate change, that sort of sense of urgency hasn't quite hit home. And as Peter says, the typical kind of policymaker sitting in Whitehall, let's say, or in Washington, will kind of shrug their shoulders and say, oh yeah, you know, climate change, we know what that's all about. We don't need any more detail. But really the problem is no different to the one that numerical weather prediction faced in the 1970s, that we know we've got a system that's really not good enough for guiding proper, you know, decision-making about, in the case of weather, about whether to evacuate a town or a city or such like that. We knew in the 1970s we could do a hell of a lot better. And, you know, with the funding that was received, we did a hell of a lot better. And that's the state we're in now with climate change. We know we can do a hell of a lot better if we have the resources, but we're struggling to kind of make the case to these, you know, the funding bodies and the policymakers and so on, and the politicians, that it's just as important to be able to, you know, assess, for example, whether Pakistan is going to be affected by these floods in the future, or actually whether they will become less likely as the dynamical effects of climate change, and other places, you know, will suffer the brunt of dynamically induced climate change. So you know, we're in a frustrating position where we know we can do better. We know that the amount of money is not, I mean, Peter mentioned something like $200 million or so a year would be a kind of probably a realistic level of what's needed to get this kind of CERN type center going. Perhaps it could be funded at a philanthropic level, but probably a mixture of public and private money would be optimal. I don't know, but it's just that we know we can do better. We know we have to do better. We know the science. We just need the tools to make it happen.
And just to be clear, I mean, there's lots of like adjacent opportunities. There's even business opportunities. The weather prediction market is now a huge opportunity for businesses. You know, there's many companies that even want to replicate what we do traditionally in institutionally funded weather prediction centers at private level. You know, big companies like Microsoft or IBM are after this. There is a lot of spin-off possibilities as well for you know, if you transpose this to climate projection level. The other thing I want to mention is, you know, we have a lot of challenges, and one is to achieve this critical mass of funding and governance. Let's not be naive. In Destination Earth, I certainly see that, you know, from writing up the scientific ideas and the science case that Tim has just explained, the associated computing, data handling, machine learning case that we spun or have published as well. to then implement, if somebody says, I give you the money, do it, to then turn this into an effective and cost-effective, but also effective in terms of results, project is by no means simple, you know. So it's certainly something that we're well aware of, and I see in Destination Earth, it's not trivial to do at all. Certainly, if you work with funding arising from the European Commission, you know, it's a democratic process. It has lots of lots of points of let's say a deceleration, but it is possible. And I think we certainly need to look also beyond Europe for creating that critical mass. There's certainly opportunities in Asia. There are certainly opportunities to collaborate directly with America, so Canada, the United States. There's strong Asian countries in Japan and China. But there's also others that are certainly very concerned about climate change hitting their country, like India, where there's enormous potential, intellectual potential, but also funding potential to contribute. So we certainly need to elevate this from the European to the global stage.
Peter, Tim, thank you so much. We have a couple questions that I've collected from some of our speakers in the audience. We have about 10 minutes left, so I'm going to start with one question, and if you guys are brief, then we might move to some other questions. We are continuing to develop new mobile technologies, 5G, 6G. These technologies and devices could create enough electronic noise on radio spectrums to reduce forecasting skills and distort computer models needed to predict weather and the progress of climate change. What needs to be done to balance the needs for connectivity without impacting our abilities to understand and predict challenges like climate change? Whoever wants to.
I think that's about the water vapor, 5G water vapor interference. Peter, do you want to talk about that?
Well, if it is, then yes, it's an observatory. So a network of mobile phones certainly is an observatory in many different ways. There's opportunities. There's also challenges for using these types of data because of the data ownership, which is with private companies. So getting access to that data in near real time, which is critical, and ideally free, is an issue. The data has to be made anonymous so that individual users or mobile phone owners can't be tracked. So there's a couple of challenges, but we certainly are looking into new devices and commodity devices, car sensors as well, or mobile phones, helping us to observe the Earth system in addition to what we presently use from satellites and stations and balloons and things. So I hope that addresses what the question is about.
Thank you. Tim, do you want to add anything?
I mean, perhaps I misunderstood the question. I thought, I mean, there was something about noise from 5G, and I thought perhaps that referred to some of the concerns that 5G could disrupt some of the, satellite sensors, particularly in the microwave part of the spectrum, which I think is a legitimate concern, but I think people are aware of that, and hopefully...
Yes, it's aware but not solved. If it's about RFI, so radio frequency interference, we have had examples where mobile phone, but also other types of sensors, some even used by the military, interfere with the satellite signals and actually obstruct our view onto Earth. There's the International Telecommunication Union, I think, that regulates the access and protection of frequencies. These are always tough negotiations because frequency bandwidth is money, and we try to protect certain areas from such interference. Sometimes successful, sometimes it isn't successful. But there's also, even beyond that regulation, problems sometimes that even if certain bandwidths are protected, that adjacent transmitters leak into our areas and pollute our windows. So it's an issue, certainly, but it mostly relates to the sensing of surfaces. So surface characteristics like land, sea ice, and these things. But it's an issue.
It's certainly a problem or potentially a problem for weather prediction, where getting very, very accurate initial conditions is super important. But for these long-term climate predictions, it's not the same type of problem. So it's not really so much a direct problem for the types of climate simulation issues that we've been discussing this
Okay,
afternoon.
thank you. Another question is, will or how will you attempt to factor in the interplay between various social and human conditions and the climate modeling? And there's a sub-question, to what extent are we actually doomed no matter what?
Well, I don't
you want to take? Yeah, you take it, Tim.
We're not doomed. I don't think we're doomed at all. I mean, we don't know yet, of course, whether future climate change will be catastrophic, which it could be, or something we can deal with. Actually, I mean, there are big uncertainties in the about future climate change that this project is trying to address. Actually, I've totally forgotten the first part of the question.
So first, how will you factor in the interplay between various social and human factors?
Well, that is important, and Peter's talking about digital twins, which is a sort of captures the idea of trying to bring in the human side, the impact side, the human interaction. But I mean, one has to bear in mind. I mean, sometimes in the language, if you like, that we use, we don't talk so much about climate predictions as projections, and we say if we continue to emit, CO2 without regard for future climate change, then that's one scenario where temperatures could be potentially very, very much warmer than they are now. But there's another scenario where we do take account of these forecasts, if you like, and really cut back on our emissions. We move to net zero by 2050, and then climate change will be not so bad, but it'll still be there and it'll still be an issue for sure. So it's a bit like COVID. The pandemic, the epidemiological modelers, in a way, didn't make predictions. They made projections about how many deaths and hospitalizations there would be if the government enacted a policy of laissez-faire where there's no attempt to curtail human interaction. And then against that, this is what the deaths and hospitalizations will be if there's a strict, cut back on human interaction. And in a sense, the philosophy underlying climate prediction is a bit like that. We make forecasts that are predicated on certain policy decisions about our carbon emissions. But on the other hand, trying to model more and more of the social interactions, I think, is part of the overall kind of scheme that the digital twin philosophy tries to espouse. So Peter probably can talk a bit more about that.
Let's have a last sentence.
Last sentence for me is just keep an eye on Destination Earth. Just follow us if you have suggestions for how we can advance our ideas towards what we're proposing here. Please become part of it. Destination Earth is based on partnerships, so it's an invitation to join, and so that we can build something, a breakthrough capability, and go beyond the critical mass.
Thank you very much. We're going to continue this discussion at our roundtable Destination Earth in an hour's time, where we will be also joined by our speaker, Frédéric Baudry, who up until last year was the Director of Technology and Acceleration at CERN. So a round of applause for Tim Palmer and Peter Bauer. Thank you very much.